in this video we're looking at the inference procedure again, a confidence interval to compare two population means when the sample sizes are small and we assume that the population variances are unequal. So that's important. The population variances in this example are unequal, the sample sizes are small, we're doing a confidence interval to compare two population means. All right, so the data step, is the same. We have a table value step here. We have a margin of error step. We have a confidence interval step. So those basically are the same. You'll notice that when we had the small sample size procedure before and we assumed that these population variances were equal, we used a pooled estimate for these quantities here. So we had SP squared, S sub P squared, right? But now we're using the 1 and 2, in other words, just the sample values derived from the original data, right? We're just plugging those in directly into the formula, which is nice. That makes that a little bit easier. The difficulty comes in calculating the degrees of freedom for our t table value. So we have two scenarios to consider. The first scenario is when the sample sizes are equal. If n1 and n2 are the same, then the degrees of freedom can be expressed simply as n1 plus n2 minus 2, which is the same degrees of freedom we had before. So that's really helpful. So when the sample sizes here are equal, we have a small sample size scenario, the population variances are considered to be not the same, then we have a simple degrees of freedom formula, use this margin of error formula, and voila, finish the problem. So that's kind of nice. We like, if they were going to assume that these are not equal to, then we'll use this approximate approach to the t-distribution in this problem, because remember, when these are assumed to be unequal, we can only approximate the distribution of our point estimator as being a t-distribution. It's just approximately t. But it's okay if the degrees of freedom is this simple formula, and that happens whenever the sample sizes are equal, right? If n1 and n2 are the same, we have the simple degrees of freedom formula, simple margin of error formula, simple final step to the problem. So that's like the ideal case. However, a lot of times n1 and n2 are not the same. And that's the case. We're going to use this Satterthwaite approximation that was developed sometime in the 40s. And when you use that approximation technique, the degrees of freedom become pretty difficult. So let's look at that set of formulas actually to get the degrees of freedom. We'll call the degrees of freedom in that case this Greek letter ni or nu, depending on how you pronounce it. But either way, that Greek letter is going to represent our degrees of freedom, and I'm going to give you the formula over here for it. So this formula will give you the degrees of freedom. It's a pretty complicated formula. It's actually a complex fraction. So what we're going to have is basically this term here, this S1 squared divided by N1. We're going to have that added to S2 squared, or S sub 2 squared, divided by n2. Both of those added together and squared in the numerator of this degrees of freedom formula. Then from there, when we finish with that, we're going to have two more terms here at the bottom. We're going to have s1 squared divided by n1, quantity squared, over the degrees of freedom n1 minus 1, plus a similar fraction on the other side here, s sub 2 squared divided by n2, quantity squared divided by n sub 2 minus 1. So it's a pretty ugly formula. All that just to calculate the degrees of freedom for the t-distribution that we're going to use in this problem. And we still have to mention one other thing, which is that we should truncate the results. Truncate the results. To truncate means if it's any kind of a decimal, you just chop off the decimal part, or essentially it's like rounding down in every scenario. So this hardly ever turns out to be a perfect integer. So if it turned out to be 47.89, we would just call it 47, right? Even though 47.89 should go up to 48, we don't do that. Just chop off the decimal part, call it 47. If it's 46.12, just call it 46, right? So that's how you calculate the degrees of freedom. So this is kind of a worst case scenario. Whenever you have a small sample size problem, the population variances are assumed to be unequal. You have to approximate the t-distribution and use this as your degrees of freedom. Everything else about this four-step procedure remains the same though. Same data step really, same t-table value, except for you have a new degrees of freedom. Margin of error formula, pretty straightforward, pretty much what we did before in the past. And then, the last and final step doesn't change at all. Just the point estimator minus the error, the point estimator plus the error, so that's pretty easy. The real horrible part is this part here, the part where you have to calculate that degrees of freedom. And in many cases, doing the calculation doesn't change all that much. And sometimes the degrees of freedom turns out to be the same as it would be otherwise. That'll happen occasionally. So either way, in either case, though, that's the proper procedure when you have a small sample size scenario and you cannot assume equal variances. And we also have different sample sizes, right? Okay.